I came across something this week that I have to say genuinely stopped me in my tracks.
Oh, yeah.
We talk about rare resources, but
hmm
imagine a planet right here in our own solar system where the rain is pure, solid diamond.
Right. It sounds like science fiction, doesn't it? Like some kind of futuristic gold rush novel.
Exactly.
But it's established, verified planetary science.
Uh,
And that's what we're digging into today. We're doing a deep dive into Neptune. So, for anyone listening who wants that, quick but thorough download on some truly mind-bending physics, this is for you.
Absolutely. This is one of those facts that delivers that immediate aha moment. It just makes you rethink everything you thought you knew about our own cosmic backyard.
Okay, let's unpack this. Our mission today is pretty straightforward. First, we need to understand the extreme science that even makes this possible. How can a gas giant rain diamonds?
Right.
Then we'll get into the scale because the numbers are staggering. We're talking trillions of tons.
Hmm.
And most importantly, we need to see why these falling diamonds might actually be the key to solving a huge planetary mystery.
Okay, let's start at the very beginning because my first reaction was just total skepticism. How does a gas planet, which is mostly hydrogen and helium, suddenly start making diamonds? Where does the carbon even come from?
That's the perfect question, and the answer is all in the atmospheric mix. Neptune is full of methane.
CH4.
Exactly. Methane, CH4. It's a hydrocarbon, so it has those essential carbon atoms. That's your raw material.
So the methane is the fuel, but I'm guessing the engine is the planet's interior itself. What kind of conditions are we actually talking about here?
Oh, the conditions they're almost unimaginable. As that methane sinks deeper and deeper into Neptune's atmosphere, gravity just compresses it to an insane degree.
And the heat.
The temperature climbs to around 7,000 degrees Celsius.
Wow. Okay, so that's hotter than the surface of the sun.
Right, hotter than the sun's surface. And the pressure, I always find the pressure figures are the hardest to really grasp.
Me too. It's just a number.
Think of it this way. It's millions of times stronger than the pressure you feel just, standing on a beach. And under that immense heat and that crushing pressure, the methane molecules they're violently torn apart.
So the bonds just break.
They don't stand a chance. The hydrogen atoms split off and the carbon atoms are freed. But they're immediately forced to rearrange themselves into the tightest, most stable structure possible.
Which is diamond.
Which is diamond. It's an instant conversion driven by pure physical necessity. The carbon goes from being a gas to a solid crystal, and then it starts to rain down.
Okay, if the process is that instantaneous, that powerful, we have to talk about the quantity. Because this is where the science just goes off the charts for me. We're talking about a little flurry of diamond dust or something more.
It's a flood, not a flurry. You have to understand, the models of Neptune's structure suggest there are entire layers of the planet made of this stuff.
An entire layer.
Which is why scientists have even coined a term for these massive reservoirs inside the planet.
What do they call them?
They're literally called diamond oceans. And that's not just a clever phrase. It describes these vast layers of solid and extremely high-pressure liquid diamond.
Okay, wait, hang on. Liquid diamond. That can't be like liquid water, can it? What does that even mean? Is it molten?
It's a distinct phase of matter. You have carbon under such intense, super hot pressure that it becomes this, metallic liquid. Think of it less like water and more like an extremely dense, super hot, viscous syrup, but it's all carbon.
And the solid diamonds are raining down through that.
Exactly, sinking through this bizarre deep sea layer of liquid carbon.
That is just incredible. So this brings up the obvious thought experiment. If Neptune has trillions of tons of diamonds.
And that's a conservative estimate.
Right. So what happens if we could somehow bring just a tiny fraction of that back to Earth?
The diamond market collapses instantly. The whole concept of rarity is just gone.
I just find that hilarious. You imagine a future where people are using diamonds for, I don't know, cheap industrial drills or ball bearings because they're actually cheaper than high-grade steel?
That's the reality of the scale. Neptune is constantly producing more diamonds every single second. It makes more diamond material in a year than all the mines on Earth have produced in centuries. It breaks any kind of Earth-based economic model.
Which brings us to the question that anyone thinking critically about this has to ask. How do we know this? I mean, we haven't sent a probe to drill down there. We haven't brought back a Neptune diamond. How can scientists be so certain?
It's a really classic case of combining observation with experimentation. First, we had the data from the Voyager 2 mission decades ago.
Right, the flyby.
That flyby gave us the ingredient list. It told us exactly how much methane was there, how the planet's mass was distributed, It gave us the foundation.
But knowing the ingredients and the conditions is one thing. Confirming the reaction is something else entirely.
Precisely. And that's where the lab work comes in. Starting around 2017, and then it was refined again in 2020, scientists at places like NASA basically recreated a tiny piece of Neptune on Earth
How?
with incredibly powerful lasers.
Lasers to make diamonds. Okay, now it really sounds like science fiction.
It's the peak of high-pressure physics, really. They take a tiny bit of methane in this highly controlled chamber, and they just blast it. And this laser blast creates that 7,000-degree temperature and the immense pressure for just a fraction of a second.
And in that tiny fraction of a second,
They got diamonds. Tiny little diamond crystals formed instantly. The carbon separated from the hydrogen and solidified exactly as the models predicted it would.
But wait, isn't that still a bit of a leap? I mean, you made a tiny speck of diamond in a lab. To go from that to assuming there are entire oceans of it inside Neptune?
It's a necessary scientific leap. The experiment validated the mechanism. It proved that, yes, this chemical reaction happens under these specific conditions. And since the Voyager data tells us those exact conditions exist across a huge part of Neptune's interior, and we know the methane is there in abundance, well, you can extrapolate that the process must be happening constantly across that entire region of the planet.
Okay, so the physics is sound, the experiment checks out. Let's pivot to why this matters, beyond just being an amazing fact. How does this solve a real planetary puzzle?
It connects directly to the planet's heat. These ice giants, Neptune and Uranus, are known to be much hotter inside than they should be, just based on how much heat they get from the sun.
There's an anomaly, an internal heat source.
Right. And this diamond rain might be that source.
How does falling diamond create heat? Is it friction?
That's an excellent way to think about it. It's an engine of energy conversion. Remember those deep viscous layers we talked about? The liquid diamond ocean?
Yeah, the super hot syrup.
When trillions of tons of heavy, solid diamond crystals are sinking through that incredibly dense material, the amount of friction they generate is just immense.
So it's constant kinetic energy being converted into thermal energy. The diamonds are literally dragging their way down through the planet's gut, and that dragging motion heats everything up.
Exactly that. This constant gravitational settling acts as a planetary-scale internal heat engine. It explains why Neptune is still so warm inside, billions of years after it formed. It's an active, ongoing process, and it's all driven by falling gemstones.
That is just such an elegant solution, but we have to contrast that beautiful idea with the reality of the place. Neptune looks like this stunning blue marble from a distance. But what's it actually like where this is happening?
It is a complete hellscape. I mean, the idea of diamond rain sounds beautiful, but the planet itself is utterly unforgiving. The atmosphere is toxic, and the weather. Neptune has the fastest sustained winds in the entire solar system.
What are we talking?
They can reach 2,000 kilometers per hour.
Unimaginable.
If you could somehow survive the toxic gas and those winds, which would just tear you apart, the pressure and gravity down in those diamond layers would crush you flat, instantly, like a steamroller on a soda can. It's the definition of planetary violence.
So what does this all mean then? You've got this world with literally an unthinkable fortune in diamonds.
Trillions of tons.
And the very process that creates that treasure is also what's keeping the planet's heart warm. But it's all happening inside this incredibly chaotic, crushing, deadly environment.
And that's the real takeaway, I think, that profound tension. It shows that sometimes the most beautiful, perfect things in the universe, these flawless crystals, they require the most violent, high-energy conditions to even exist. You need that immense destruction and compression to get that kind of perfection.
It really makes you reconsider what wealth even means on a cosmic scale. The diamonds aren't rare at all. It's just the journey to get them that's impossible.
Indeed. And maybe that's the thought we can leave you with today. When you look out into the cosmos, just remember Neptune. The prettiest things in the universe are so often locked away in the deadliest places, and that's a tension we're thinking about wherever you look.